Ayeva my name is Abram. This is a lovely show, a Learn Extra Live. Of course, it is a lovely Tuesday. What's
Yeah.
up, Tinyiko?
I knew you would start that way and we try again. Aye, Makaina. Yeah, it's
This
all.
one, umfukile.
Nipukile mjani but
Nami naifukile.
it's
Ikhenza
all.
ukubona yena, loko ibona yena yatsaka.
All right.
Yativa ukuri ito Johnza.
All right, good. Now, Nico, Nala, we're going to have a good lesson in physical sciences, and of course, we'll be talking about mole calculations. We're continuing to talk about mole calculations today as well. Yeah.
Awesome.
It's all about.
It's one about I can't support. Well, my sisters, thank you for tuning in. Really love you guys and appreciate your time. Pre-matriculants, there's no more time now to play around. All you need to do is to learn more and learn extra with us. We've got notes, tons and tons of notes from the first term up until right now. All you need to do is to jump into learn.mindset.co.za. Download all of them, view all of them. They're for free. They're for you guys. So use them. Otherwise, we'll post you links to today's notes on facebook.com/learnextra and also on Twitter. Follow us at learnextra. I'd love to chat with you guys and find out how was your day at school if you were writing. How was the paper? Did you nail it or was it the other way around? But as Mindset says, I trust you guys. You will never be beaten up by any paper because you're always equipped. But remember, also on Facebook, we'll post you the Test Yourself link to the Test Yourself questions. If you answer them correctly, you stand a chance of winning this awesome Casio calculator, proudly sponsored by Casio. I'll be announcing last week's winner later on the show. Mr. Tinyuk, over to you, Put.
Thank you so much, Abram. Like I said, we're talking mole calculations today, so we're continuing with what we have been doing from the previous lesson. Okay, so we will be talking about mole calculations, doing some revision on that, because really we've been talking about this for a long time now. We will also be discussing what we call the limiting and the excess reagents. Remember that when we say reagents, we can also call them reactants. Okay, we're still talking about the same things here. And we'll also be looking at how to calculate for percentage purities and percentage yield. So we'll be looking at those calculations here. We'll also look at how to solve problems that are related or relating to empirical and molecular formulae. You know that we've got empirical formulae and molecular formulae, so we will see the difference between them and see how to calculate and find out those two types of formulas. All right. Now, here is your challenge question, and it is packed today. 25 grams of magnesium burns completely in oxygen, right? So magnesium is reacting with oxygen here. You have to write down in A the limiting reactant or reagent, okay, in this reaction. B, you need to write down a balanced chemical equation showing how magnesium is burning in oxygen. C, you need or you are asked to calculate the mass of magnesium oxide that is formed. And D, if 38 grams of magnesium oxide is formed, calculate the percentage purity of the magnesium, all right? And lastly, calculate the percentage yield. So here you're talking percentage yield, okay? But up here you're talking percentage purity of the magnesium sample. So good luck with your challenge question. I hope you will find your way through it and be able to get the answers to that. If you really work logically enough on that one, I give you a thumbs up. And I'm saying you will be, you are ready. You are a good science learner who is ready to nail those exams like Abraham was saying when we started. Let's move on. When we're talking about moles, remember that moles are quantities of substances. We're talking about the quantities of substances here. And these quantities obviously are the quantities that are taking place or that are actually involved in those chemical reactions. From what we have done earlier on or in previous lessons, we know that if I'm given the mass of a substance, I can find the number of moles which is denoted by small letter n by when I divide that given mass by what we call the molar mass. Remember that that capital letter M there is for molar mass, whilst this one here, the small letter m, it's the given mass. So if I've got given mass, I can calculate for the molar mass making use of this equation here. But if I'm talking about gases and I'm told that I've got these gases under standard conditions, which is standard conditions of temperature and pressure, STP, I can use this equation here to find my number of moles. And how does that equation work? All right? This Vm here, it's what we call the molar volume, which is constant at STP. So molar volume at STP. All right? Which is what? 22,4 22,4 cubic decimeters. Should be just cubic decimeters. All right. Cubic decimeters per mole. Okay, so 1 mole will occupy that. Where this part here, or the top part, this small v here, would be talking to what we call the given volume. So I can still find this number of moles, n, making use of this formula here. And this is only when we're talking STP, when we're talking that, when it's a gas and we're talking that it is under conditions of standard temperature and pressure. Now the other part, or the other level of it, when we're still talking number of moles, we can look at concentrations and make use of that formula to find the number of moles. From this formula here, we know that this one, C, is the concentration. I will use the capital brackets to say concentration, okay? And N, again, is what? Moles. It's what we're looking for. And here is the volume. V is the volume of the solution. Okay, so this is what I can use. And remember, if I'm working using this concentration equation here, this one, this concentration equation, it says that concentration is number of moles over volume. If I want to find the number of moles will be concentration times volume. So I can use that. It is all about the number of moles here, this N. It's all about the number of moles. So we are trying to look at all possible options of calculating for the number of moles. Okay, now, limiting and excess reagent. What is a limiting reactant or reagent? A limiting reagent is completely used up in a chemical reaction. Nothing of this substance remains after the completion of the reaction. So when we talk of a limiting reagent, we're talking about that substance that will be completely changed in that chemical reaction. But the excess one is the one that will remain. We would still have some quantities of this excess reagent because now it has got nothing more to react with, because now the limiting reagent has completely been used up. That's what it means. So when we talk this excess reagent, this one is not completely used up in a chemical reaction. Okay. And when we come to the yield, yield is the amount of product formed. Okay. If we want to know the percentage yield, we look at the actual yield divided by the theoretical yield multiplied by 100, and therefore we find the percentage yield. Now, quickly, what is this actual yield? Actual yield means when a reaction takes place, all right, we know at the end that we have produced so much. Say nitrogen is reacting with oxygen to form nitrogen dioxide. The yield is how much of the product we are having. When we balance that chemical equation, we can calculate how much of the product we're going to have if we are given the quantities that are reacting. But that is called the theoretical yield. What we calculate making use of the chemical equation is called the theoretical yield. But if the reaction takes place and we find out that instead of what we calculated to be the quantity of the product that should be formed, according to how the substances are combining in their ratios, we find that less of it has been produced. That less of it that has been produced, which is actual, is what we are seeing. We put it up here. It is the actual yield. We divide that by our theoretical yield, which is our calculation. And we multiply that by 100%, and we have now found what we call the percentage yield. Okay. We're going to do examples, of course, later on to show you more on how this is done. Percentage composition. Here, by percentage composition, this is something that tells us about the amount in percentage of an element or a compound in a substance. For example, the percentage composition of sulfuric acid. Okay, so you've got sulfur, you've got, in sulfuric acid, you know you've got this. You've got hydrogen, you've got sulfur, you've got oxygen. So we find how much of each of these elements is in a molecule of sulfuric acid. First, you find the molecular formula of, the molecular mass, the molar mass of sulfuric acid. How do we do that? This is sulfuric acid. 2 to 1 for hydrogen, 32 for sulfur, 4 into 16 for oxygen. And that works out to 98 grams per mole. All right? Find the percentage of each of this. For hydrogen, we have got 2 out of that 98 times 100. That is the percentage. For sulfur, we have got 32 over, or out of the 98 times 100, it's 32.65. And for oxygen, we have got 64 of 98 times 100. And then we find that the percentage is 65. Empirical and molecular formula. Empirical formula is the simplest ratio of elements in a compound. Percentage composition of a substance by mass is used to determine what we call empirical formula. For example, let's look at this one here. A substance contains 36.5% sodium, 25.4% sulfur, and 38.1% oxygen by mass. If it is by mass, so we can convert these percentages into grams. We can say this is mass. Okay, and when we do that, we say that let's find out, because our compound contains sodium, sulfur, and oxygen, but we don't know what are these values here. So we just say X, Y, Z. So for sodium, we say, okay, it's 36.5%. So it's 36.5 grams divided by the molar mass of sodium, 23. It gives us 1.59. We do the same for sulfur. It's 25.4 divided by 32. It gives us 0.79. For oxygen, we do the same. It's 38.1 divided by 6. It gives us 2.38. And the ratio is therefore 1.59, this is sodium, and then 0.79, this is sulfur, 2.38, this is oxygen. Okay, then at this point we take the smallest ratio here, which in this case will be that one. Okay, and we divide through all of this to simplify the ratio. When we do that, we find that 0.79 goes 2 times to 1.59 for sodium. It goes once to itself for sulfur, and it goes 3 times to 2.38, this one, for oxygen. Remember, this is sodium, sulfur, oxygen. This means that the empirical formula for this substance containing sodium, sulfur, and oxygen will be this one here, Na2, this one. And then sulfur, all right, it's 1, that one. So there's 1 there. And oxygen, it's 3, this one here. So that Na2SO3 is the empirical formula. This is the empirical formula as we found it there. Okay. Right, so, and lastly, if we are to find what we call percentage purity, okay, this percentage purity is calculated using the mass of the compound divided by the mass of the sample, okay, multiplied by 100%, and we know we've got that percentage purity. All right, let's hand back to Abram, and let's hear what he has from the mindsetters over there.
Well, the messages are enjoying the show. I'll take some of your comments and shout outs after the break when I announce the Test Yourself winner from last week's show. So in the meantime, you have the challenge question on the page. It's waiting for you guys. The Test Yourself questions are also waiting for you guys. So you've got so much to do during this break. We'll see you after it. Welcome back, pre-matriculants. Now, the winner from our last week's show for this awesome Casio calculator is
Amukelani Mnisi.
Well done. Congratulations to you, Amukelani Mnisi. This awesome Casio calculator is coming your way. To be like Amukelani, all you need to do is to test yourself with the questions that we have, answer them correctly, get all of them correctly on time, and then you could be our next winner. So guys, the ball is on your court.
All right.
That's what most teachers normally say.
They would always say that
I've done my part. I taught you guys.
The ball is in your court now. Yeah.
Well, guys,
Right.
send your questions through. Though we're here to help you so that you do not point fingers when things don't go your way. We told you, we're here for you.
Okay. Right. Thanks, Abram. I'm gonna go straight now to our section that talks to improving your skills. Let's see how you are supposed to approach some of these questions here. Question number 1 says 8.4 cubic decimeters of nitrogen reacts completely. Oh, that's a key word. From what we have been talking about, you should be thinking twice about that word there. It reacts completely with hydrogen to produce ammonia at STP. All right, so this is at standard temperature and pressure. We know what happens there. We know what that condition is about. Question number A. Which substance is the limiting reactant? The limiting reactant is that substance that is used completely in a chemical reaction. And because it is used completely, this other one do not have any other thing to react with. So it has limited the reaction. It caused the reaction to stop there and then because it was no more. All of it was gone. So in our question here, we are told that nitrogen reacted completely. So because it reacted completely, nitrogen is our limiting reactant or limiting reagent. Okay. Number B says, write down a balanced chemical equation for this reaction. we know and we are told that this is nitrogen reacting with hydrogen. We know these are gases. The result is ammonia. Ammonia is NH3. Balance the equation. You would see here that we have got 2 nitrogen atoms. We only have 1 there, and for that reason, we will put a 2 here, so that we have got a balanced number of nitrogen atoms left to right. But by putting this 2 here, we have done something to the hydrogen that is there. It is now 2 times 3. We have got 6 hydrogens on the right, so we need to make it 6 on the left as well. For us to do that, we need to put a 3 here, so that 3 times 2 gives us the 6. So the chemical equation is balanced in that way. All right. Now, moving on to question number C, we are asked to calculate the mass of ammonia produced in this reaction. Now, for us to calculate for the mass of ammonia produced, we will need to know how much of ammonia was produced in terms of moles. That is going to help us find the answer to this question. For us to do that, we go back to what is given to us. We are told that we've got 8,4 cubic decimeters of nitrogen. And this reaction occurs under STP. Now, it means I can calculate for the number of moles of nitrogen. Okay? And nitrogen, remember, is the limiting factor. So if I calculate for the number of moles of nitrogen, in this case, because it's standard temperature and pressure, I would use this formula here that says number of moles equals to given volume divided by molar volume. Okay, why am I doing that? Because I'm given the volume of nitrogen. So I can actually work out the number of moles in that volume of nitrogen. So number of moles of nitrogen in this volume will be equal to 8, what? Let's see what it is up there. It's 8,4 cubic decimeters. 8,4 divided by the molar volume at STP of a gas, 22,4. And how do we get the answer there? Here is our calculator. We've got 8,4 dividing that by 22,4. And what's the answer? Okay, we've got 0,375 moles. 0,375 moles of nitrogen. Now, all these moles of nitrogen have been used up. If it has been used up, according to our equation here, or chemical equation here, for every 1 mole of nitrogen, 2 moles of ammonia will be formed. So if the number of moles that have been used for nitrogen, okay, it's 0.375. The number of moles of ammonia that will be produced will be twice the number of moles of nitrogen that has been used, because this one tells us that for every 1 mole of nitrogen used, I'm going to have 2 moles of ammonia formed. So I can say that number of moles of ammonia formed or produced, this will be equal to twice the nitrogen moles used. I'm writing so that you see or you understand where all this comes from. Okay, 0,375, and that will be equal to, what is 0,375 times 2? Just multiply that by 2 and we get what it is, 0,75 moles. Okay, so 0,75 moles. 0,75 moles of ammonia have been formed. Now, the question wants us to find the mass, not the number of moles. But for us to find the mass, we will then need the molar mass of ammonia, and I'll show you why later on. Now, molar mass of ammonia, okay, molar mass of ammonia, right, it's fine, don't have my periodic table here with me, but let me see, it's 14 for nitrogen plus 3 into 1 for, so it's 14 for nitrogen plus 3 into 1 for hydrogen. So this works out to be 17 grams per mole. Okay, that is the molar mass. Why am I doing this? Okay, why am I doing this? I'm doing this because I have to use a formula now that would push me or would want me to use the molar mass to find the mass. Which one is that? If you remember well what it is, it says number of moles equals to given mass over molar mass. Okay, and from here then I can say that this number of moles for ammonia, remember I want the mass of ammonia, number of moles for ammonia, it's this one here, 0.75. So I can say 0.75 then equals mass divided by the molar mass, which is 17. All right, and from here we can see that mass will be equal to 0.75 times 17. Let's see what we get here. So we can just take our answer here and times 17. And what do we get? 12.75 grams. So the mass of ammonia produced is 12.75 grams. Okay, so we have answered this question here, the question on calculating the mass. Okay, now coming to question number 2. All right, calculate the percentage water of crystallization in copper sulfate. The formula of crystallized copper sulfate is CuSO4 5H2O. All right, for us to find the percentage of water of crystallization, and remember that water of crystallization, we have to take that whole part there. All right, we again start by finding the molar mass of copper sulfate 5 waters. So we have waters in science here. Now, how do we find that? Cu 63.5 plus S is 32 plus oxygen 4 into 16 plus water, I know it's 18 when you work it out, so let me just say 5 into 18 there. All right, so please check your periodic tables to find all the values that I'm putting in there. They are from the periodic table. Okay, just don't have it to display it for you here, so we see all those. When you work this one out, you should be able to get, let's see here, can do this here, say 18 times 5, okay, that's 90, so 4 times 16 is 64 plus 90 plus 32 plus 63.5. What do we get? 249.5. So we've got 249.5. 249.5 grams per mole. Okay? When we have that, we can find the water, the percentage water of crystallization, which will then be what? Percentage water of crystallization will be equal to 90 divided by 249.5 times 100. And that will work out to be, let's just check on it here. So it's 90. Okay, so this is 90 divided by 249,5 times 100. And what do we get? 36.1%. 36.07. So 36.07%. That is the percentage water of crystallization in hydrated copper sulfate. Okay, now coming to this one here. It says the percentage composition by mass for a compound is given below. Determine its empirical formula. You see here you've got potassium, there, and there. So you've got potassium, you've got chlorine, you've got oxygen. So for potassium, it will be 32 over 39. All right, this is potassium. And for chlorine, it's going to be what we have there, 29 over, this must be, what is this one here? Chlorine. Don't have my periodic table with me here. This should be 30, is it 31.5? Let me not even take a chance here. I don't want to mess up, but I'll show you how it works out to be at the end. All right, just don't have my periodic table with me quickly. So this will be for your chlorine. Okay, so let me just do that. We'll get it later on. Chlorine. And then for oxygen, it's 39 over 16. Okay, and that is oxygen, right? You work out all these values here. Making use of your calculator. Let's just get these other ones here. 32 over 39 gives us 0.82. So this one is 0.82 for potassium. I know that this one is also going to work out as 0.82 because I worked out the solution. All right. And the last one, let's just get it quickly from the calculator. It's going to be 39 divided by 16. All right. And what do we get? That works out to be 2.44. So this is 2.44 for oxygen. Now, for us to find the empirical formula, you divide or you simplify. Okay, to do that, you divide by the smallest ratio, the smallest value in your ratio. Okay, and what is the smallest value? The smallest value here is the 0.82. So if you divide by 0.82 throughout, uh, 0.82 with there, you're going to get a ratio that says 1:1:2. Let's just work out 2.44 divided by 0.82 divided by 0.82. What do we get? We get 2.93. Now remember, with empirical formulas, the values we're getting here, we need to simplify them in such a way that we don't have commas at all. So 2.9 is basically 3. So we'd write that as 3 here. And what will then be the empirical formula here? The empirical formula is going to be, remember this is for potassium, K, and 1, so it's K1. The next one is chlorine, so it's Cl1, and the next one is oxygen. Oxygen is 3. So that is the empirical formula of the substance we were talking about here. Now look at it. This is potassium chlorate, okay? And as it is, it's actually giving us both the empirical formula and the molecular formula. So what we need to know is that with the empirical formula can give us the molecular formula, but the molecular formula is not necessarily the empirical formula. So in this case, we were lucky to find the empirical formula, and that formula happens to be the final formula for the substance that we were looking at. So that's it. From the questions that we were looking at, or the questions that we had to practice working on and see how to solve these problems here. Let me hand back to Abram.
Thanks. I have some comments on that question. I think we'll tackle them after the break.
Okay.
So Mindsetters, I am aware of what you guys are saying on the page.
Yeah.
But after the break, we'll treat all your questions.
Okay.
Welcome back, Mindsetters. Now, a quick reminder, if you missed any of our notes, you know where to get them. You get them on lan.mindset.co.za. I'll post the link also on Facebook. But now I think it's time for us to get to the challenge question.
Sure. Now, let's come to the challenge question of the day. And thank you to Mindsetters. They were able to see or remember that the molar mass of chlorine is 35.5. Okay, so that we would have divided by 35.5 here. All right. Remember, you don't have to memorize these values here. You need to know how to use your periodic table. So thank you for that one. Now, moving on, coming to the challenge question. Let's look at it. It says 25 grams of magnesium burns in oxygen completely. That is a key word again. Right? A, write down the limiting reactant in this reaction. Obviously, it is magnesium because it is the one that reacts completely. It is consumed completely. It is finished completely at the end. We don't have any magnesium anymore, but we still have oxygen. So oxygen is our excess reagent, whilst magnesium is our limiting reagent. Okay, so that's how you need to understand these things. And moving on, coming to number B, write down a balanced chemical equation for the above reaction. Balanced chemical equation for the above reaction, you've got, so this is number B, magnesium solid reacting in oxygen. You need to know how to come up with a formula for magnesium oxide. Group 2, Mg2+. Oxygen group 8, group 6, so you've got 8 minus 6, or 6 minus 8, you've got minus 2, so they work out to be just that. So this is a solid, this is of course a gas. All right, balancing this equation, you need a 2 there because of this oxygen. When you put a 2 there, then magnesium also has to get a 2 on the left here as a reactant. Okay, moving up. Coming to question number C. Calculate the mass of magnesium oxide formed. Now, for us to find the mass of magnesium oxide formed, if we have 25 grams of magnesium, okay, 25 grams of magnesium has burned completely. If I work out the number of moles of magnesium here, from the equation, 2 moles give me 2 moles. So these are equal moles. Now, if I have 25 grams of magnesium, how much moles of magnesium do I have? I need to use this formula here. Number of moles equals to given mass over molar mass, and that will be equal to Given mass 25. Molar mass magnesium should be 40, I believe. Let's just work it out here. Okay, so I've got 25 divided by 40. And what do we get? 0.625. So I've got 0.625 moles. Okay, 0.625 moles of magnesium. Now, what is the mass of magnesium oxide formed? Need to get the periodic table here. Really need to get the periodic table here. Let me just find out. Wonder if I... Okay, so for magnesium oxide moles formed. All right, that should be the same as that. Should be 0.625. How do I get to that? Okay, because the ratio here is 1:1. 2 moles of magnesium will yield 2 moles of magnesium oxide. So you simplify that, it's 1:1. So if I had that number of moles, it means if I had that number of moles, it means I'll produce equal number of moles there. For magnesium oxide, let's find out the molar mass of magnesium oxide. That will be equal to 40 plus 16. And that will be equal to 56 grams per mole. Right? Now, if I've got 56 grams per mole for molar mass of magnesium oxide, it will mean that from this formula here that says number of moles equals given mass over molar mass, I can say that my number of moles is 0.625. That will be equal to mass divided by the molar mass, which is 56. Therefore, the mass of magnesium formed will be equal to 0.625 times 56. 0.625 times 56. Okay, and what is that? Let me find out. 0.625 times 56. I'm getting 35. Something. Yeah. All right. So that gives us 35 grams. Okay, 35 grams. All right. Another way of doing this would have been to say 2 times the mass of that and 2 times the molar mass of that, which would have been was actually going to lead us to the same answer here. But going on, because we have answered this one here now, number C, calculate the mass, okay, of magnesium formed. If 38 grams of magnesium, that's 38, should not have been this way. Okay, fine. Now, let me go back to this here, to this one here, come back to this one here, and see where we might have gone wrong. That is the mass of magnesium oxide formed. If that is the mass of magnesium oxide formed, okay, what would be the, let me come down here. I think there's something that is not working that well here. Let's go back to magnesium plus oxygen, giving us magnesium oxide. My periodic table is letting me down here. Now, this is when you have balanced this chemical equation. So you'll have 2 times, in terms of mass here, you'll have 2 times 40, okay, and you will produce 2 times 40 plus 40 plus 16, that's 56. So 2 times 56 is going to give you 2 times 56 gives you 112. Okay, so that gives you 112. So what we're going to have here is 56, and you get 112. So what we're going to say here is that 80 gives us 112, and 25 gives us how many? Sorry, I'm going to use an X there for what we're working on. All right, so X for the number of the mass of magnesium that has been produced. And of course, this is going to give us exactly 35. So what I'm going to do here is to change these into 32. All right, now, number D, okay, number D, if we have changed that into 32, number D says, find or calculate the percentage purity of magnesium. So if I've got 32 here, and what I calculated theoretically, I found it to be 35. The purity of magnesium will be that if I've got my 80 is to 112, and I would say how much of magnesium initial did I start with to give me the 35, okay? So 80 out of 112 should be equal to X, which is the actual mass of magnesium out of 35. So I'm just using ratio and proportion here to do that. So X equals, let's just make use of our calculator here quickly. All right, so let me just use the fraction. I think that will be quicker. So this will be equal to 80 times 35 divided by 112. Okay, and what do we get? We're getting 25 here. So we get 25 grams of magnesium. All right, now if we have 25 grams of magnesium, all right, and yet we had produced 35 of magnesium oxide, what will this be? Let me just come back to it. Okay. So we produced 35 grams of magnesium, and how much of magnesium oxide, and how much of magnesium did we have? So we found it to be 25, and we are to find the percentage purity. Now, percentage purity here, percentage purity will be equal to the actual mass, all right? Actual mass divided by the theoretical mass. Theoretical mass, okay, times 100%, okay, or let me not use that here. I think that will be not so up. So that the mass, this will be the mass of the sample, mass of sample, okay? So that works out to be actual mass. What is that? We found it to be 25. Sample said we had 25. You multiply that by 100%, you get 100% sample. So that sample there was all composed of magnesium. There was nothing that was something else there. So even in this case here, where we have produced 35 grams of magnesium oxide, if we are to look for number C, we're calculating for percentage yield. Remember here, the percentage yield will be the actual yield divided by the theoretical yield, like I said earlier on. So the Ilya formula that I wrote there was actually for the last part. I believe you're going to have time to work on that. I should have actually brought the periodic table here. It actually messed us up and took much of our time. So always make sure you work with your periodic table.
Exactly.
All
Thank
right.
you so much, sir. Really appreciate it. Unfortunately, we have to end it there.
And the questions, we couldn't attend to them.
Yes, but
Yeah.
remember, my sisters, there's a help desk that is dedicated to help you guys. All the links and information will be on Facebook. We love you and thank you for today. Peace.